Welcome to the sixth week of the live interactive session on the course Integral Transforms and their applications. Today we will continue the discussion on Mellin transform and Hankel transform. Like last week, we have seen some simple problems, and today we will see some advanced problems based on these two transforms. So let us start. So first of all, evaluate the Mellin transform of the function, which is given as a series. It's a summation overall integer k greater than or equal to 1 e raised to minus kx divided by 1 plus e raised to minus 2kx. So we can write the function as k is equal to 1 to infinity e raised to minus kx divided by 1 plus e raised to minus 2kx. So now we need to take the Mellin transform. So Mellin transform of any function f of x, let's say from variable x to s, is given as f of x times x raised to s minus 1 dx integral 0 to infinity. That's just the definition. So here the function is actually given in the form of a series. So what we can do is that we can simplify the function. So if we directly want to apply the Mellin transform, let's say the Mellin transform of the function f of x, because of the linearity we can take the summation outside, so it will be k equal to 1 to infinity. Now we want to take the Mellin transform of e raised to minus kx divided by 1 plus e raised to minus 2kx, right? So this kind of combination we don't have in the table of the Mellin transform series. So what we can do is that we can simplify this a little bit. Basically, if you observe this particular form, exponential of minus kx divided by 1 plus e raised to minus 2kx, especially the denominator, which will be like so 1 plus some quantity exponential of minus something, and for any positive value of x and k, you will see that is actually less than 1. Like basically e raised to minus 2kx will be less than 1 for k positive and x positive numbers. So we can use the binomial expansion. So this we can write e raised to minus kx into 1 plus e raised to minus 2kx the whole raised to minus 1. So now using binomial expansion, we can write this as e raised to minus kx and series over minus 1 the whole raised to m e raised to minus 2kx m is equal to 0 to infinity. So this is just the binomial series. Okay, so now we come back to this definition. So what we want to do is that Mellin transform of the function is equal to sum over k equal to 1 to infinity. Now Mellin transform of so before that, again we can simplify this, like bring the exponential of minus kx inside the summation m equal to 0 to infinity minus 1 the whole raised to m, and group together the exponential of minus kx. So we'll get this minus kx times 2m plus 1. Okay, now we'll substitute that here. So Mellin transform of based on equation 1, we are substituting for exponential of minus kx divided by 1 plus e raised to minus 2kx, this series, which is m equal to 0 to infinity minus 1 the whole raised to m e raised to minus kx times 2m plus 1. Now again, based on the linearity, we can bring the summation outside. Okay, so m equal to 0 to infinity minus 1 the whole raised to m. See, the Mellin transform is applied over the variable x and to some variable s. So m is actually a constant, depends on that, and the Mellin transform is just going to act on exponential of minus 2m plus 1 k times x. Okay. Now, from the properties of Mellin from the tables of Mellin transform, we know that exponential of Mellin transform of exponential of minus x, which is just gamma function, right? It's gamma of s, and Mellin transform of the property, it's a function of ax. We know it is a raised to minus s times Mellin transform of the function itself for any a which is greater than 0. So if we combine the both, we can find that Mellin transform of exponential of minus ax for any positive constant a, we will find that it will be a raised to minus s times Mellin transform of exponential of minus s, which is just the gamma function. So we use that in the second equation. So from in the second, we can see that we need a Mellin transform of an exponential with a being the constant 2m plus 1 times k. So we can just replace that using this result we have here. So the summation terms will remain the same. And now the Mellin transform, we can replace it as 2m plus 1 times k, the whole raised to minus s, times gamma of s. So now we can see the summation is actually taking place over the so actually this is k equal to 1 to infinity. Okay, yeah, so the summation is taking place over ki and m only. So s is basically a constant according to summation, so we can bring the gamma function outside, and also the summation over k, so we can group the summation over k. So we can see k is only appearing here, right? So so we can bring that like k raised to minus s, and then summation m equal to 0 to infinity, it's minus 1 the whole raised to m, 2m plus 1 the whole raised to minus s. So again, if you recall, this is by definition so basically if you see the summation over k and summation over m are now independent. I mean, there is no variable k appearing inside the summation m, summation of m. Basically k and m are splitted, the summation over, so we can just write them as product of two summations. And if you recall that the first sum is actually the definition of zeta function, the well-known Riemann zeta function, and the second one probably you may not remember. So it will come like something like, if you expand the first summation, zeta of s is 1 minus 1 by 2 raised to s, 1 plus 2 raised to s plus 1 by 3 raised to s plus etc. That's a zeta function. The second one, it will look like 1 minus 1 by 3 raised to s plus 1 by 5 raised to s etc. So that is not very well known, but it's a function which is closely related to the zeta function, which has a name which is known as the Dirichlet beta function. So this is also it's a beta function, you can say it's beta of s. Do not confuse with the beta function we learned earlier, which is related to the gamma function. So there is another beta function we know, which is beta of x comma y, which is t raised to x minus 1 1 minus t the whole raised to y minus 1 dt integrated from 0 to 1. So this is actually a multivariable function. It's function of x and y. So do not confuse it with this particular beta. So this also is known as a beta function, but this is Dirichlet beta function, okay, which is related to closely related to the zeta function also. So now if you see, the result is actually gamma of s, zeta of s, then beta of s. So this is basically the Mellin transform of the function which is given. Okay, so So when I say the derivative beta function is related to the gamma function, the actual expression is beta function is actually theta of s comma 1 by 4 minus theta of s comma 3 by 4 the whole divided by 4, where this multi-valued theta function, right? Now one more complication. Now we have theta of s comma a, which is known as Hurwitz theta function. So which is basically same like we have, so just that is shifted summation. Like so when a is equal to 0, we will obtain so that is theta of s comma 0, we will obtain the actual theta function, the Riemann theta function we have. But for any finite real number a, it's like a multi-variable function. So that's just the relation between beta function and the Hurwitz zeta function. So a lot of advanced functions. Other than that, it's just the procedure is same. So is it clear or any doubt?
Yes, sir. Clear, sir.
Okay, good. So then we'll move to the next question. Evaluate the Mellin transform of the function f of x equal to exponential of minus log x squared. So while this is actually a simple problem, while doing this, so even before that you can actually realize the Mellin transform is actually closely related to Laplace transform. Even in your assignment there is actually, I think, a problem which shows that there's a relation between Mellin transform and the Laplace transform, which you were able to show. But so I will try this problem and you will see the same procedure that we have used earlier in the Laplace transform will appear here. So this is actually an easier problem. So by definition, the Mellin transform of the function should be exponential of minus log square x into x raised to s minus 1 dx, integrating from 0 to infinity. So here you can substitute ln x equal to t, so x equal to e raised to t, then dx equal to e raised to t dt, and the integration limit will change from now. So t is going to, so x is going from 0 to infinity, so t will go from log 0 to log infinity, which is minus infinity to plus infinity. So you'll see it's minus infinity to plus infinity, e raised to minus ln x squared, which is t squared, times x raised to s minus 1, so that is e raised to t times s minus 1, times dx, which is e raised to t dt. Now you can combine them, these exponential terms together, so you'll get e raised to minus t square times e raised to ts dt. Again, you can group the exponential terms together here. It's e raised to minus t square plus st dt. So now it's actually see the this particular expression you can see it's related to Laplace transform or closely related to Fourier transform. So you just need to you will be able to show that in the assignment problem. So you can see from the expression itself there is some close resemblance with the Laplace transform we had earlier. Like it's like the Gaussian function is multiplied with exponential of st, but in actual Laplace it is exponential of minus st. So there is some relation, some mapping between them, so that you need to show in the assignment. So here what I will do is that we will use a technique that we have used earlier, like completing the squares. Like we can complete this like t minus s by 2 the whole square. Then you can so it will become minus s square over 4, so we had to add an s square over 4 here. It's basically completing the squares, then the integral dt. So now you can see the exponential of s square over 4, which is just a constant which you can keep outside or take outside, then minus infinity to plus infinity, exponential of minus t minus s over 2 the whole square dt. Now you can substitute t minus s over to some u, so that dt is equal to du. I mean, you don't need to, because it's just a shifting, so the integration will become obvious. Also, the limit won't change for any real finite value of constant s. You will see this is s minus infinity to plus infinity, even for u. And the exponential of minus u square d. And this Gaussian integral is well known, right? So this is just root pi. I guess all of you know how to show that using polar coordinate system, so I'm just skipping that. So it's just root pi into exponential of s square over 4. So that's just the Mellin transform of the function which is asked for. Mellin transform of exponential of minus ln x squared. So is this clear?
Yes, sir. Clear.
Okay, good. So yeah, I think that was simple. So we will move to the next one. Now evaluate the Mellin transform of the function f of x equal to e raised to minus x minus 1 plus x, and find its region of convergence. So so first of all, okay, let us try doing this from the basic definition. Actually, that may not work, that's why I want to show it, but we will start from that basic, like exponential of minus x minus 1 plus x, then dx. Okay, x raised to s minus 1 dx, integral 0 to infinity. So this is from the basic definition, right? So we know that so we can basically expand e raised to minus x times x raised to s minus 1 dx, integral 0 to infinity, then then plus x minus 1 times x raised to s minus 1 dx, 0 to infinity. So the first one we know, it's basically the Mellin transform of exponential of minus x, which we already know it's going to be gamma function. Or if you just see the definition, you will see this is actually gamma function, right? And the convergence for this is the real of s should be less than infinity and greater than 0, then only it will be converging. But the second integral, you see that's just a polynomial, and you see for any s which is positive, this integral may not converge. Okay, I guess that is clear. Like we need a specific region of s. So let's say we take one out. So this integral also we can split. It is just if you expand it, it is just x raised to s dx, 0 to infinity, minus x raised to s minus 1 dx, 0 to infinity. So I mean, we know what is the integral of x raised to s, right? It's just x raised to s plus 1 by s plus 1, limits x equal to 0 to infinity, minus again x raised to s by s, limit x equal to 0 to infinity. And you will find that you are just going to apply the limits, like infinity raised to s plus 1 minus 0 raised to s plus 1 by s plus 1, again minus this is infinity raised to s minus 0 raised to s by s. So this is like you what you are going to get is, I mean, right now it look like complicated, but so here you have definite answer, it's a gamma function, and that these two terms are like infinity raised to basically some constant by s plus 1 minus some constant by s, and the constant is like it's infinity minus 0, and we don't want an infinite answer, we want some converged answer. That's why it's asking for the region of convergence. So from the first time example, sorry, from the okay, the first term is actually gamma function, second term is some infinite value, third term is also some infinite value. So we don't want the infinite value, so for that we can say if s is the real value of s is less than uh, 0, the third integral will converge, right? And here you can say if the real value of s is less than -1, the second integral may also converge. But issue is that again the 0 might have some singularities in that ranges. So it's particularly also the first integral converges only in the interval 0 to infinity. So these are all like disjoint set and these ranges for s, and you cannot say that this does have a finite solution in some particular interval. It's looking like it don't have, right? So what we do is that uh, we'll do the opposite, I mean the inverse approach. So let us start from the simple example, that is like what is the Mellin transform of exponential of minus x. So it's just exponential of minus x times x raised to s minus 1 dx integral 0 to infinity. And so before going to that, I just want to ask you that is this the first explanation that I have given, is that clear? Because like what I saying is that the integral can be splitted like an exponential and then a polynomial part alone. So exponential with that integral will is that we already know it is going to converge to gamma function. That's just the definition of gamma function, and that is going to happen in the interval when the real value phase is bounded between 0 and infinity. But the second integral, the polynomial integral, which don't have a definite finite value or finite answer, so that's like infinite value. So that's why we are going to do the like the inverse approach. So is there any doubt in that?
No, sir, no.
Okay. So what we are going to do is that the Mellin transform of the exponential function, like I said earlier, this is just this integral, and we know it's a gamma function, and it is going to converge in this interval. Okay. Now from the definition of the inverse, we know that so from here we can write the Mellin inverse of gamma function is actually exponential of minus x, right? So we have to show this first using the definition of the inverse transform. So that's just gamma of s times x raised to minus s in ds. Integral is from c minus I infinity to c plus I infinity 1 by 2 pi I. So this is the Mellin inverse of the gamma function, where c should be such that it should lie c should be a real number, and we are taking the integral in the complex plane. So let's say we are taking the integral over this line from z minus I infinity to c plus I infinity, where c is here. This is real of s and this is imaginary of s. So the c should be such a way that it should lie in the region of convergence, where like c should be element of, okay, for this particular case we have here the real of s is lying between 0 and infinity, so c can be any number between 0 and infinity. That will not affect the solution. So now we have the function, so the integral here, so this should give rise to exponential of minus x. I mean, we know the solution, we just want to show it. It indeed gives back the exponential of minus x. Then we will move to the small modification, so that we'll get the solution that we are actually searching for. That is the Mellin transform of this particular function. So for that we will start from here, and we will show that this indeed gives back the exponential of minus x, and we will do some adjustments. So for that, first of all, see this integral, this is actually a complex integral. So to perform this, we always do the trick like closing this on the left side and make a contour like this. So the integral, closed contour integral over, let's say this is an arc and this is the line. So the arc plus line will contribute to a closed contour. So that integral of this particular function, the function we will input later. For the moment, just, I mean, you know that there's a function. I'm just writing the integral sign only, right? So this will be just the arc plus and the line. And in like the usual cases, you can actually show that arc integral will go to 0 in the limit of the radius of the arc is going to infinity, so that the contour integral just become the line integral. That's we are seeking for. So that means c minus I infinity to c plus I infinity gamma of s times x raised to minus s ds will be just equal to the contour integral, closed contour integral of the same function. And since we want to divide with 1 by 2 pi I, we can divide both the left and right side with 1 by 2 pi I. And if you see here, this particular function, so the contour integral is performing for this total functions gamma of s times x raised to minus s, right? And if you see here, okay, this x raised to minus s, which can be written in terms of this. See, for this integral, x is actually a number and s is the variable. So we can write this as exponential of minus s ln x, right? So it's now it's a standard function. It's exponential of some constant times s. So that's a standard function. And you can see this function, basically the exponential function don't have any singularities. I mean, basically in the from the Cauchy's theorem, we need to check for whether the function has any singularities in the closed contour. So that's what our objective is. So you can see here the exponential function don't have any, because it's just exponential, right? So that don't have any singularities. And but you know, the gamma function has singularities, which have singularities at the locations at s equal to 0, minus 1, minus 2, etc. Every negative integer it has the singularity. So we have singularities at s equal to 0, minus 1, minus 2, minus 3, like that. So what we will do is that we can use the residue theorem, because there's no other singularities, only the singularities at these particular locations. So we can write it as the residues of the function gamma of s times exponential of minus l ln x for s equal to 0, minus 1, minus 2, etc. So these are all, if you check, they are all actually symbol poles. So you can find the residues just by using the symbol technique. So this, let's say this is s equal to minus k, where k is equal to 0, 1, 2, 3, etc. So what you can do is that you can multiply with s minus k and gamma of s exponential of minus s ln x and then taking the limit of s tending to minus k, where k is from 0 to infinity, basically just integers 0, 1, 2, 3, etc. for the k values. And you will find that this only the first two combinations need to be like, because the gamma has the pole, like it's gamma at any s equal to minus k behave like 1 by s minus k times some constant, some number, and you are multiplying with s minus k. So this will just cancel and you will get the constant, which is the residue of that combination. And if you evaluate that, you will find that is just the residue is actually minus 1 the whole raised to k divided by k factorial for this first combination. It's minus k times gamma of s, and then the remaining exponential of minus is ln x, which is not singular at any of s value, which is minus k. So you can just directly apply the limit s tending to minus k in that expression. It is just exponential of k ln x when s equal to minus k, and you have the summation here k equal to 0 to infinity. And now you will recognize that this is actually, so this combination is actually x raised to k, right? So you can now write it as minus x the whole raised to k divided by k factorial, so which is just e raised to minus x. So we got back the expression. I mean, what we are trying to show is that the Mellin inverse of gamma function is actually exponential of minus x when real of s is less than infinity and greater than 0. That we have shown. So this is how we can show that. Now we will modify this. So now we will come to our objective. We will do the same trick again in the gamma function, but now instead of the range we are taking from 0 to infinity, we will take the range. So you can see when we have taken the range is from 0 to infinity, the c is actually lying here, right, between 0 and infinity, so that all the singularities of gamma function, including 0, minus 1, minus 2, minus 3, everything is left side of the value c, so that it lies inside the closed contour. Now we will modify it a little bit. What we will do is that again we will find Mellin inverse of gamma function, but we will choose c to lie between 0 and minus 1, so that okay, let me draw that again. So nothing changes, only the location of c we are changing it, so that the contour only changes, but the concept remain unchanged. So what we are going to do is that it's the same color. So again here we have real of s, imaginary of s, and the singularity is 0, minus 1, minus 2, minus 3, everything is there. And I am drawing the contour here. So this is c, so this is c minus I infinity to c plus I infinity. So I am integrating over this line. So this is 0, this is minus 1, minus 2, minus 3, and then I am closing this contour on the left side. Okay. So in this procedure, I have said that c is now lying between 0 and minus 1, so that this integral just become basically, if you see the summation of residues, of the same function that we had earlier, which is gamma of s times exponential of minus s ln x. Okay, let me put a break here. Okay, yeah, so this is the same function, but now since the contour is closed on the left side and we take the c to be lie between minus 1 and 0, the only values minus 1, minus 2, minus 3, they are inside the contour and 0 is outside the contour. So according to the Cauchy's theorem or the residue theorem, we only need to consider those singularities which are inside the contour, so that we don't need to take account the 0. So this will do the trick. Like basically we can say it is s equal to, so this is basically the limit s tending to minus k, s minus minus k multiplying gamma of s times exponential of minus s ln x, where k is now 1 to infinity, unlike the earlier case where it was 0 to infinity. So everything is same, even the residues are also same. we'll find that the first combination will have the residue minus 1 the whole raised to k by k factorial. And the exponential of minus s ln x is also evaluated to be exponential of s ln k. It's a exponential of x k ln x. Yeah, but only change is that the summation is now changed from k equal to 1 to infinity. Earlier it was k equal to 0 to infinity, because including the pole at 0 also. Now we are excluding that, so this is just k equal to 1 to infinity and minus x the whole raised to k by k factorial, which you can now write it as 0 to infinity minus x the whole raised to k by k factorial minus the value at 0, which is just 1. Now you can write this minus e raised to minus x minus 1. So what we have found is that the Mellin inverse of the gamma function is now exponential of minus x minus 1, where real of s, that is basically the range of c, will appear as the range for the s real value of s. The real value of s should lie between 0 and minus 1. If that is the case, then we will get this solution. So but still we haven't obtained the question we are asked for. So this, what does this mean? This means the Mellin transform of exponential of minus x minus 1 is gamma of s again, but the range of s should be lie in this interval. So again, our question is little bit more different. So it's not just e raised minus x minus 1, but we have one more x added to it. So if you see the pattern, we will repeat it once again, shifting the c again to the left. So I'll draw the contour again. So we have a real of s here and imaginary of s here, and the poles here 0, minus 1, minus 2, minus 3. So I am again shifting the c, so the integral is performed from z minus I infinity to c plus I infinity, and the contour is now also closed on the left side. So nothing changed, only the location of the c is now changed. So this is c, this is 0, minus 1, minus 2, minus 3. Now we say that c now lies in between minus 1 and minus 2. So we are evaluating the inverse of Mellin inverse of the gamma function. So from the definition, it is some summation of the residues of the function gamma of s times exponential of minus s ln x. But c equal to the contour is the c value now lies in between minus 1 and minus 2, so that only the singularities on the left of c, that is basically lies inside the contour, which are minus 2, minus 3, minus 4, etc. Only they are matter. So again the same procedure, we are finding the residues by multiplying, because they are simple poles, we are just multiplying with the s minus k, where k is going from 2 to infinity here, all the real integers, and again the function is e raised to minus s ln x. We will find this will boils down to k equal to 2 to infinity minus 1 the whole raised to k by k factorial into x raised to k. So again you can rearrange this from 0 to infinity minus x the whole raised to k by k factorial minus, at k equal to 0 we will find its value is 1, and at k equal to 1 its value is minus 1 into x by 1 factor. So basically it's minus x. Okay. So now the first one is exponential of minus x, then you have plus x minus 1. So that's what we are asking in the question, right? Exponential of minus x plus x minus 1. So we obtained here that the Mellin inverse of gamma function is equal to exponential of minus x plus x minus 1, where real of s now should be lies between minus 1 and minus 2, which also says that the Mellin transform of exponential of minus x plus x minus 1 is gamma function again, and also the range of convergence is when s is the real value of s is bounded between minus 2 and minus 1. So that's a solution. Is this clear? So it's a long procedure. We are just doing an inverse process. So probably it is not obvious in the first slide. That's why I have explained it in this detail. Basically saying that the Mellin transform is unlike the Fourier transform and all. It is not that unique. Like you have to also specify the range over which it's valid. So you can see that the Mellin transform of three functions like exponential of minus x, exponential of minus x minus 1, exponential of minus x minus 1 plus x, all of these are gamma function, but all are valid in certain intervals only. When the real value of s is lies in certain interval, each of them will be valid. So that's all. I just thought I will just introduce this. Okay. So any question in this?
No, sir, it is clear.
Okay. So yeah. So I think we'll move to the next question then. So solve for the steady state temperature u r, z in a horizontal homogeneous slab of thickness 2L, through which there is a vertical circular hole of radius 1. The horizontal faces are held at temperature 0 and the circular surface in the hole is at temperature T0. So the equations are given. Dou square E by dou R square plus 1 by R dou E by dou R plus dou square A by dou R square equal to 0 when the boundary conditions boundary conditions, because it's a steady equation. You have in R you have one boundary condition, which is when u of r equal to 1, and for every z you have the value is T0, the temperature, and at both plus L and minus L, the extremes of the slab, you have the temperature being 0. So it's just you just need to take the Hankel transform here, right? So it's actually easier in that sense, but what is the catch here is that unlike the normal Hankel transform, that won't work here, because here the domain is actually if you notice, so R is a domain, R is a variable in which we are to take the Hankel transform. Now R is going from 1 to infinity. So other than that, nothing is. So if R was like 0 to infinity, why R is 1 to infinity? Because we are saying there's a hole of radius 1, right? So that inside the hole we don't care. Only outside the hole where there is a matter or the slab is there, where only we care. So if R is 0 to infinity, we can directly use the Hankel transform we had earlier. But R is 1 to infinity, so that Hankel transform won't work. So it's actually an out of syllabus thing. Because say the same question, if it comes with there is no hole, you can actually do, right? You just take the Hankel transform and you will use the property in the first 2 times combined. It will be just minus let's say R2, yes, you are doing the Hankel transform, minus S square times Hankel transform of u plus just d square u tilde by d z square equal to 0, and then you can solve it easily. This is just a linear differential equation of second order, and that you were able to solve easily. So here, because we have the issue of r is going from 1 to infinity, you may not be able to solve it that way. So that's why we have a modified Hankel transform. So I just thought to introduce that, so that it may be helpful in some particular cases. So first of all, we'll start with the normal Hankel transform, that the Hankel transform of order nu of a function f of r. So just f of r. So let's say r to k is that transformation is performed. So it's f of r into j k of r into r dr from 0 to infinity. Now see, the j is basically Bessel function of order k, is solution of a Bessel differential equation, and Bessel differential equation is actually second order differential equation, and which have two orthogonal solutions. So Bessel function jk, Bessel j, jk of r, okay, I think we made a mistake. Yeah, in the definition it's actually j nu kr. Sorry, I made a mistake. Okay, so this j nu are the, so let's say j0, j1, j2, or integer orders, or any other order. They are one set of solutions. Okay, so for a particular differential equation with the nu is fixed, you will get j nu of r as a solution. So if you plot them, let's say j0, j0 will look something like this. Okay, so this is j0, should be symmetric. Symmetric. Okay, and j1 will something like this, which goes to 0 at the center, and then j2 goes like quadratic, then everything has amplitude decaying. Okay, so this is j2, so like that it will go, and you have one more set of solutions. So these are, let's say, for a fixed nu value in the differential equation, you have these are the solution. Now another set of solutions are y, so they are Bessel y. So that you have y0, which goes something like this, and then y1, which also looks something like this. All of them has a property that all of them are singular at 0, and in the negative value they don't exist, they will go to complex plane. So this is basically I am plotting versus r. Okay, all of them I am plotting in the radial coordinate. So these two set of solutions together are, the two independent solutions of, so every second order differential equation will have two orthogonal independent solutions. These are the two independent solutions of the Bessel differential equation, which is a second order differential equation. Now a kernel, so here you see in the normal Hankel transform, here we see the kernel is actually j nu kr, where y doesn't appear because y is anyway singular at the location 0. But when we want the integral to be from 1 to infinity, let's say in a finite domain, we don't want 0 to be included, we need to eliminate some region 0 to 1 or something. So for that we need to use a different kernel, which is Weber kernel of z nu, which is a function of s and r. We'll call it as so this is Weber kernel. So basically it comes from the integral which is given by Weber. So basically z nu of s comma r is actually a combination j nu SR times y nu S minus y nu SR times J nu S. So using this we can define the new transform, which is actually Weber transform. Let's say I will write it as Hankel transform. It's a modified Hankel transform with a W here denoting the Weber transform of index mu of some function f of r. So let's say nu to r to s, I am changing the variables. Okay, so this integral will now this transform is defined as, it's actually like earlier, it's a r times f of r. Instead of Bessel function j, we use this combination Weber kernel. It's a z nu of s comma r then dr. Okay, let's say this is not s, this is k. Let be consistent with the earlier definition. And then r is integrating from 1 to infinity. So now you can see that the integral is performed in a finite domain from 1 to infinity, unlike earlier. So that the boundary conditions you need to apply at 1 and infinity. So any problem, so in this particular problem we have asked it to do this the domain is r equal to 1 to infinity. Let's say you have a problem where this is not r equal to 1 to infinity. Let's say r equal to some number, let's say 5 to infinity, or some generally some positive number a to infinity. So what you can do is that you can scale r with that particular number and define some r prime, so that r prime will go from again 1 to infinity, right? So this you can always do, so that you scale appropriately. You will always scale down to this this transform. But this you cannot do like you cannot do the scaling to reach 0 to infinity. That's why we always need this particular kernel to achieve this particular domain, like 1 to infinity or some finite number to infinity. So we need this kernel, Weber kernel. Okay, so the inverse of this particular transform you can get back. Let's call this as f capital F nu of k. So you can get back the function f of r using the inverse k times f nu of k. Now unlike the normal Hankel transform, here also z nu k comma r exists, but okay, let's say dk. You also need to do one more modification here. It's j nu of k square plus y nu of k square. Now k is from 0 to infinity. So notice that here r is actually 1 to infinity. Okay, but k is now integrated from 0 to infinity, because that doesn't matter. K is just a wave number space, right? R is a physical space. Physical space we have restriction from 1 to infinity. Wave number space doesn't need to, which have a 0 to infinity value. Also, unlike the forward transform, the inverse has a modification that you have a denominator that need to be accounted, so that the inverse will work. And now this has a property. The property only will enable us to solve this kind of problems. Like we have a heat transfer, basically the diffusion operator, the combination of derivative, basically the Laplacian operator in the axisymmetric coordinates. So that we want to see how that is getting transformed using this particular Weber transform. So h nu of some function g double prime of r plus g prime of r by r minus nu square over r g of r. So according to the normal Hankel transform, we would expect this to be minus k square times the Hankel transform of g. That's all. No boundary values will appear, but here you see there is a boundary value need to be appear, which is 2 over pi times g of r equal to 1. I don't know the boundary. The other boundary assuming that the function is vanishing, where g is tending to 0 at the other end. So this is a transform we are going to use. So that this is a property, like we can use that property. Our equation is this. We are just going to use that. So let me write the equation again. So it's dou square u by dou r square plus 1 over r dou u by dou r plus dou square u by dou z square, which is equal to 0. So where u is a function of both r and z, we are going to take the Hankel transform. You can see here, because we have only it's a axisymmetric derivative, so, in the polar coordinates, we only need to take the transform with the nu being 0. Like earlier we have done j of 0, same, so h of 0 here, the Weber transform. And let's say this will convert to u tilde of k and z. So now we take the transform, we will see it's from the property it is just minus k square times u tilde of k z. I'm not writing the explicit dependent on k and z, or let's say I will write u of k and z. Then we are using the equation 1. Okay, so from equation 1 we will see we have to use the boundary correction to it, which is minus 2 over pi the u evaluated at r equal to 1 for r z, plus then we are see the Hankel transform on the remaining term, which is a derivative of z, so that does not affect how it appears here. So just d square u tilde by dz square, which is equal to 0. So now you just rearrange it. So you will find d square u tilde by dz square minus k square u tilde is equal to 2 by pi, and this is actually given at r equal to 1 for every z. Its value is actually T0, the temperature is. So we'll just use that. So this is just a second order differential equation now that you can solve, right? U tilde is just some a cos h k z plus b sin h k z minus 2 T0 by pi k square. Let me check, is that correct? Yeah. So this is how you can now you need to apply the remaining boundary conditions, which are these two at at z equal to plus l and z equal to minus l. You can apply these boundary conditions, and you'll find that the solution will be u tilde is equal to 2T0 by pi k square times cos h kz divided by cos h kl minus 1. So that if you take the inverse, you will find u of r comma z is just 2T0 by pi integral 0 to infinity 1 by k cos h kz by cos h kl minus 1 into z0 k comma r divided by j0 of k square y0 of k square multiplied with dk for every r which is greater than 1. So this is how you will get the solution. So is this clear?
Yes, sir, it is clear.
Okay. Okay, so then for today we'll stop. So we'll meet next week then. Okay, thank you.
Okay, sir. Thank you, sir.